Alright, and welcome back everyone, and this is the Chip Master, and I'll be in this video I'll be giving you a full timing analysis of the Lenovo. Right, this is the NMA272. This is the Lenovo G50 series, I believe, yes, and this is the Intel Haswell platform, right, single CPU. Right, I have here an image of the single CPU that I'll be tracing out. I'll be giving you the full timing analysis of this Intel Series 5th and 4th and 5th generation single CPU. As you can see, this is the CPU core and this is the PCH core. Okay, and yes, and this is the PCH core and this is the CPU core. Right, so this is two chips in one physical package. This is a BJ package, as you can see, which is has a diameter pair, yes, of a parameter of a 40 by 24 millimeter, and it is Intel MCP Haswell 15-watt CPU. Right, and as you can see, we have the different connections, such as the RAM. This is 1.35 volt DDR-L with a low voltage RAM, 1.3 volts. It's the memory bus. It's a dual channel, so it's 2 slots, see, up to 8 gig per DIMM. Okay, I won't go through this block diagram exercise. This is in the paid videos, so I'll just focus. I'm giving away this full. This is up to 4 classes. This to explain the entire timing of this chipset, from inserting the adapter all the way up to the CPU gets it reset signal, takes up to 4 classes. Each is actually each over 1 hour and say 15 to 20 minutes per class. Right, so that's how long one class will be, 1 hour and 15 to 20 minutes. Alright, so let's get started. And first, when we are checking depending on the schematic, you know, for the isolation protection and charger. Alright, so we type charger. Okay, and charger page is the insertion of the adapter plugin. Alright, and this is the protection isolation page, and this is the adapter and battery connection page. Okay, so we will start from here. As you all know, this is the battery connection, and this is the adapter connection. And I'll be using this program, the diagram designer, and I'll sketch out the entire timing sequence step by step in the order in which you're going to use to check during the maintenance process. So this is the process of how I will use to create my timing diagram, full timing analysis. Alright, so first this is the adapter interface. As you can see, JDCIN1 or JDC-in1. Right, as you can see, pin number 1 and 2 supply, pin number 3 adapter ID, pin number 4 and 5 this is grounded, as you can see. So we have a fuse here, we have 2 EMI filtration coils and some coupling capacitors for EMI filtration. After passing through this EMI coil, it produces the V-in section, right? V-in, as you can see. So this is V-in, this is adapter interface name, right, after coming through these EMI coil and capacitors. So you have a fuse here. You know, Lenovo always uses a fuse at the right at the connector of the DC jack. There will be a small fuse, and this is to protect. The fuse basically acts as a protection or to isolate the circuit from the AC power or any form of EMI filtration, right? So this is why we call it EMI, right? It stands for electromagnetic interference. Okay, after passing through these coils, it produces V-in, right, and V-in is then passed, as you can see, through the protection and isolation page. So this is the charger page, as you can see, a charger, which is protection isolation. Alright, so this is the charger page, as you can see, with the charging IC, which is BQ, right, BQ24737, right, very popular charging IC. The BQ series are Texas Instruments charging chip, as you can see. Now after V-in passes through the adapter interface and then renamed to V-in, it comes to this page. As you can see, we have V-in, which is coming through this 2 MOSFETs. These are 2 MOSFETs, and these are your protection and isolation MOSFETs, right? So we have PQ301, we have PQ302, and as you can see, the arrow is pointing outwards, right, from the base or the gate. Then it's, you know, it's a P channel MOSFET, right? So this voltage of V-in, it is 19 volts coming from the adapter interface. As you can see, it's coming to the drain pin of this PQ301 P channel MOSFET. At the same time, it is flowing as you can see, there's a small diode. This is a body diode that's inside of this MOSFET, and it is conducting from anode to cathode, and then it is exiting to the source of this PQ301 pin and producing P2, as you can see. So P2 is produced right after passing through this P-channel MOSFET, right? A04407, very popular PNP MOSFET, and this MOSFET is conducting through the small diode that's inside, right? And remember, each car diode has, if you don't know, right, each diode have a voltage drop of about 0.7 volts. So 19 volts subtract 0.7 volts, that's leaving us with what? 18.7 volts. Right, depending on the charger, you will get sometime 18.7 to 18.8 volts. All right, so this is their adapter detection after coming through this first diode, because remember, no matter what voltage this voltage has at the gate here, it could be 18 volts or it could be 6 volts, it still will conduct, because this is forward bias. This diode is forward bias, so automatically will just flow through, and then it will become P2. So no matter what voltage the gate is on this MOSFET, it will flow this 18.7 or 18.8 volts. Okay, so P2 is produced, right? And then this diode, as you can see, if you notice, the diode is in reverse bias. So that means this MOSFET won't, so the voltage will stop here. So the voltage will stop here. All right, so this diode will it will stop at the anode, the cathode of this diode, and waiting for a switch signal. So at this time, this is another P-channel MOSFET. So if this voltage is 18 voltage, then it will cut off. Right, this MOSFET will cut off because it's not conducted, right, because it needs to be switched on. So this is acting as a switch. So in order for this MOSFET to switch on, can anybody tell me how can we get this MOSFET to switch on? By looking at the schematic, what the schematic is trying to tell me, or to tell us how to, in order to get this MOSFET to be switched on. Right, as you can see, if you notice, we have here a signal here, which is PACN, and this is a signal that it's coming, it is generated from the charger IC section, and it is coming to this MOSFET of PQ307B, and we have another MOSFET here which is PQ307A. So this is a 2-in-1 MOSFET, but in physical appearance it's one. And we have a resistor here, as we see, it's PR307 of 68 kilo ohms, and we have another resistor here of 200k, which is PR203. So we need, so in order for this to conduct, this MOSFET gate must be pulled to about 6 volts in order for it to conduct, because this is a P-channel MOSFET. So the voltage at the gate should be what? Right, the voltage at the gate should be less than the voltage at the source in order for it to conduct. So this is a P-channel MOSFET. So if this voltage is, if the voltage is 18 volts, then it will cut off. Right, MOSFET completely cut off. Right, so in order for it to work, it must be 6 or lower. It must be at least 6 volts minimum. Alright, so this signal PAC in, so in order for this signal to be generated, it has to come from this charging IC, right? And there's some working conditions that we must know in order for it to produce this signal, AC in, PAC in signal. Right, so this is our charging IC, as you can see, and I have here a data sheet of a similar page of this charging IC, as you can see. Right, and it's a BQ 24725A, and it's a 1 to 4 cell lithium battery SM bus charge. Right, so this is a completely SM bus charge charging IC, and it communicates with the IO controller in order to detect the battery temperature, the battery capacity, right, the brand of the battery, right, and other parameters of the battery, and then it will start charge once the battery meets the working conditions. And there's no overcurrent and there's no over temperature, then the battery will charge. Right, so this is a battery notebook battery charging IC. As it says, it's found in notebook computers. It's a low voltage, right, automatic N channel MOSFET selection system, power source from adapter or battery, driven by internal charge pumps. Right, and as you can see, it is for notebook computer systems. See, portable notebook computer systems, right? Handheld terminal, industrial and medical equipment, portable equipment, etc. All right, so let's go to the pin definitions of this chip. Right, we have some set of pins here on these chips, as you can see. Right, VCC, we have AC detect, we have ACOK, we have SDA, cell SCL, SDA, I out, and so forth. So all these are inside of the pin definitions of this chip, right? So on here on this page it says pin configuration and functions, right? So we have the pin number 1, which is ACN, right? So let's see what this says. And pin number 1, this is a input current sense resistor, negative input, right? Place an optional 0.1 microfarad ceramic capacitor from ACN to ground for common mode filtering. Right, and it's the same for input current sense for ACP. Input current sense, this is the adapter circuit detection current sensing circuit, right? And it is as of ACP to ground from common node filtration. Place a 0.1 microfarad capacitor from ACN to ACP differential mode filtration. All right, SRC, this is the charge pump source, right? The input, right? On this charging IC, the CMP out, right? It's the same. Right, it's an input pin, and this is getting, normally in some boards this would be AC, this will be getting 19 volts from here coming all the way to this chip, right? And this chip is getting this voltage, right? It's coming to this pin as an input pin, right? And that's 19 volts, and it is being amplified, by the charging IC to output 25 volts. So let's say these two MOSFETs were NPN transistors, NPN MOSFETs. If these two MOSFETs were NPN MOSFETs, then this pin would become active because it needs to receive this 19 volts from this section, right, from here. In order for it to conduct P2, this voltage would come and be connected to this pin. At the same time, when this working condition is met, AC VCC's condition is met, right, AC detect condition is met, AC OK, and the linear output of 6 volts is met, then it will drive an output of 25 volts to conduct these two MOSFETs gate, right? So these two MOSFET gates will be, and they will be turned on and fully conduction to produce the 19 volt to produce B plus, right? This is their common point. I'll explain this shortly. Alright, so let's go back to the schematic, to the data sheet, right? The next one, so AC drive charge pump source input, place a 4K resistor or 4 kilo ohm resistor from SMRSC to the common source of AC FET, right? So the common source of AC FET is right here. This is the AC FET, this is their AC FET, and this is their RB FET, right? AB, AC, and RB FET. So these two MOSFETs are your AC and RB FET. So this is acting as a fuse. This circuit is acting as a fuse. So instead of using the other fuse on the adapter page, before that fuse to get a spike, then it will hit this MOSFET first. This is your AC FET. Most times when you have a dead or no power state laptop motherboard, then and you check isolation protection, you normally find this MOSFET broken, or if there's any overcurrent or there's a shorted cap on the 19 or the common point rail, then this MOSFET will be damaged because this is your AC FET. So this is acting as a isolation and protection to protect. So it is easier to replace this MOSFET than to replace your CPU, right, which is more expensive, right, and it's more easier to repair by just replacing this MOSFET, and the motherboard will be up and running again. So this is acting as a fuse, and that's why it's called protection and isolation circuit. Isolation means that in battery mode, these two MOSFET will be isolated or cut off so that your battery can what? Your battery, see, BATT, this is coming from your battery connection. So your battery will discharge. As you can see, the diode is forward bias. The forward bias, right? Our diode is forward bias. So this voltage will flow and come out, and then it will go to the common point, which is the B plus rail, to produce, right, as you can see, to produce B plus. Alright, so this is the common point. Okay, So let's go back to the datasheet pin definition. Right, we have AC drive. Right, so AC drive pump output to drive both adapter input N channel, right, AC FET and reverse blocking N channel MOSFET or RB FET. Right, voltage is 6 volts. If AC drive voltage is 6 volts and above, same as when the voltage of AC detect pin is between 2.4 to 3.1 volt, then the voltage on the VCC pin is above under voltage lockout protection, then the VCC pin is 275 millivolts and above, right. SRN pin is so that the AC FET and RB FET can be turned on to power the system by AC adapter. Place a 4 kilo ohm resistor to the AC drive to limit the input current rush. So normally you will put a resistor before. So this pin, right, so this is placed before the AC FET. As you can see, based on what the data sheet is telling us, that in order to get this voltage to this, you will put a resistor here, right, to limit the input current rush to the charging chip and connect it to this pin. Okay, so this is the process. But because these are 2 p-channel MOSFET, that architecture is not used. So I'll explain. Right, this is not used, so these are 2 p-channel MOSFETs, so you don't need this voltage. AC drive, you don't need this because this voltage is up to 25 volts, and if 25 volts is going to these 2 MOSFETs, it will cut off, and the motherboard, the board will be dead, and it can't power from adapter, hence the battery won't charge, so it will be in a dead state. So this needs 6 voltage, not 25 volts. Okay. Alright, so let's go back to the data sheet again and let's move to the next pin definition. AC detect, adapter detection input. Right, program adapter valid input threshold by connecting a resistor divider from adapter input to AC detect pin to ground. When AC detect pin is above 0.6 volts and VCC is above UVLO, which is under voltage lockout protection, then the REGN, this is a LDO, low dropout voltage of 6 volts. Right, and ACOK comparator and IOT are both active. So the IOT pin is basically the total amount of system power that's generated, and that is reported to the IO controller through pin 7 here. Right, so this is reporting to the IO controller EC. This is going to our EC to determine the amount of current, total power, and if there's any overcurrent taking place, then through the SM bus it will stop the charging and turn off the 2 switching MOSFETs. Right, this is your upper MOSFET, this is your lower MOSFET. These will stop switching, so it will pull, drive high and drive low, switch off, hence battery won't charge. So you get plugged in, not charging, if there's any overcurrent taking place through these pins. So this pin is reporting to the IO controller, the EC, the total amount of power that is generated by the system. Many times this capacitor will short. This is a 100 ohm resistor, see, 100p, right. This is a 100 picofarad resistor. Alright, 100 picofarad resistor. This is a very high precision capacitor. If this capacitor is faulty, battery won't charge. So replace this capacitor. Many times this fault will happen and your battery will be charged. Okay, I've seen it many times where this capacitor starts to leak and loses its capacitance and causing not charging. Alright, so that's the IOut pin. Alright, next one, IOut pin, adapter, charge current output, selectable with SM bus command. Alright, IOut voltage is 20 times, so this is multiplied 20 times by the output voltage of the, so this is the positive and this is a negative. Right, so it is calculated internally, as you can see, and it is multiplied 20 times to give you the difference in the amount of pressure drop based on the amount of current generated when you turn on the laptop motherboard. So this is multiplied 20 times, right, 20 times multiplication. Right, that's in the charging page when I'm charging section when I'm teaching the laptop notebook charging analysis. That's for paid. I cannot explain in this one because that one is for paid video. Right, I'm teaching full timing analysis, not charging class. This is not a charging and circuit analysis class where I focus entirely on what are some of the possible causes of not charging fault. This is a timing. I'm teaching the Lenovo G50. This is the NMA272 timing, full timing analysis. All right, this is part one. All right, next week I give next free class. Only one free class I will give. This is for reference and to see what you are getting when you purchase full. All right. Okay, so all right, that's the charge I/out pin. Next we have SDA SM bus open drain data, which is connected to the IO to SM bus data line for the host controller. The host controller is the EC, or the IO controller, or smart battery connect. So the smart battery and the IO controller, they share the same line, and they are connected to a 10K pull-up resistor in accordance to the SM bus for communication. And same for the SCL, right? SM bus clock input, connect SM bus clock line from the host controller or smart battery, connect a 10K pull-up resistor according to the SM bus specifications. Alright, so let's go to the next one. This is the ILM charge current limit program, and it is being connected by a resistor divider, which is a system reference 3.3 volt rail to pin to ground. The lower of ILM voltage or digital to analog limit sets the charge current regulation limit to disable control. Right, so this is another charge control current detection output for input, for the charging IC, right? And back drive, this is the charge pump output to drive the system battery to turn on the battery in battery mode. So this is their battery discharging signal from the charging IC, right? And this voltage is very important in battery mode. Right, there have SRN, there have SRP. This is the current sensing detection resistance and signal for the battery in battery mode. Right, so as you can see, charge current sense resistance negative input for battery, right, sensing, and at the same time this is the charge positive. So this is N for negative, this is for positive, right, as an input indicating the battery total amount of current and charge current, right, connected to a 0.1 capacitor current sensing resistor. Right, we have digital, we have power ground. This is a ground to ground the chip. If this is not grounded, chip the charge in the chip won't work. Right, LO drive, this is a low MOSFET drive, right, signal to drive the lower end channel MOSFET gate. REGN, this is a linear voltage of 6 volts coming out of the linear regulator. Very important. The LDO is active when voltage on AC detect pin is above 0.6 volts and the voltage on the VCC is above under voltage lockout. Connect a 1 microfarad ceramic capacitor from RGEN to ground, and as you can see, RGEN is here and it is being connected by this 1 microfarad capacitor, and at the same time it is going through a Zener diode to be boost. This is the boost strap. Your boost circuit consists of a diode, a resistor, and a capacitance, and this is known as your RDC circuit to boost the voltage. Right, the voltage has to be boosted in order to drive this upper MOSFET. Right, and in a PWM class I will explain the whole concept of the boost. So it is connected here. So boost coming through this anode to cathode, this Zener diode, and it is coming to here, and it is going to pull up this, and this voltage at the gate here, it's supposed to be 25 volts. Right, this is in the PWM class I will explain the whole process of a PWM circuit and how it works, right, and that's in the paid videos, so I cannot explain it in this part of the class. Okay, so let's finish. We have boost, see, high side power MOSFET, and connect to a 0.047 microfarad capacitor, a boost to phase, and a boost strap Schottky diode from RGEN to boost. So that's the Schottky diode. This is here. This is to boost the voltage, right, and it is connected to the gate, a resistor and a capacitor to the phase angle. At the same time it is connected to high drive. Right, so that's this is known as V boot. This is called V boot. Right, and I will explain all about the V boot in my PWM class, in the paid class. Right, so let me start sketching this diagram. So as you can see, our adapter circuit is adapter. The input is here, and this is known as JDC in 1. So let's select it. Alright, so this is a square tip, a rectangular tip, so I'll just draw a rectangular box here. Alright, so this is JDC in 1. Alright, so this is outputting from here. Alright, and this is coming out as V in. So this is V in. Adapter output name adapter interface V in. So after adapter V in coming out, it is coming through 2 P channel MOSFET. Alright, and that's right here, connected to this line. Alright, and this is our 19-volt rail coming through, connected. Alright, so these two MOSFETs are going to be controlled Alright, I'll just move this. Let me zoom in. This is how I'll teach my classes. I'll give full timing with diagrams sketched out for you. This is how I teach when I'm doing timing, full timing analysis. Fed a bit down. All right. And this is going to be outputting from here. Okay. Alright, so that's the adapter. Going back to isolation protection, and we'll copy this first MOSFET, and that's PQ. The first one is PQ301, and the next one, this is PQ302. Alright, we have a charging IC. Alright, so this is step 1. It's okay. Alright, so step 1. I'll give this a nice Alright. Alright, step 1. Let me carry the entire section down a little bit. Alright, so that's step 1. Alright, so the next part, as I said before, we're going to look at the working conditions of the charging IC. So as you can see, P2 is being generated here, and P2 was generated from here. After coming through the first MOSFET to the body diode to become P2. So this same P2 is coming through our resistor, and at the same time it is being charged with this capacitor, so it is delayed, and it is coming at the same time to pin number 20 VCC, and this is 19 volts. Remember, this is not a pressure drop. This is not a pressure drop because it's not coming through a diode. Normally on some board you'll see two diodes here, an R diode, one from the battery and one from the adapter, and that will drop the voltage to about 0.7 to about 18.7 volts or 18.8. There's no diode, so there's no pressure drop, so it is 19 volts coming through this diode. Sorry, this is 18 volts, sorry, because this has a pressure drop. So this 18 volts is coming through, 18.8 volts coming through that diode of this MOSFET, of this internal, there's a body diode inside of this MOSFET, dropping the voltage to 18 volts. That was my mistake, very sorry, I'm sorry. So it is coming through this resistor to limit the input current rush. At the same time, it is delayed. See, as you can see, it's delayed. So this is a 10k resistor, so 10k, right, multiply by 1, right, so it takes approximately 10 milliseconds. Right, so 10 milliseconds to come and power this chip, and this is to prevent any input current rush, limit the input current rush, right? So as you can see, VCC, input power supply diode or from adapter, right? It is input supply from a diode or from adapter or battery voltage using a 10 ohm resistor and a 1 microfarad capacitor to ground as a low pass filter to limit, right, the inrush current. So this is why this resistor is placed here, and to limit the in current, limit the inrush current, sorry, right, is there to delay the inrush current rush, right, inrush current, limit it, it's limited, right. All right, so that's 18 volts, 18 volts coming through this section to power our charging IC. Right, at the same time, V in, as you can see, this V in is coming from our adapter section. It is coming through a voltage divider, another voltage divider. All right, so it's two resistors. A voltage divider consists of two resistors, one connected to the supply and one is connected to the ground to pull down from a higher voltage to a lower voltage. So this voltage, as you can see, is coming through two resistors. After conduction, it becomes 737 underscore AC detect. So this is this charging IC is a BQ. Right, so as you can see, it's BQ24737, as you can see. So that's the name of the chip. This is the version of it, right, and it can be substituted, right. So that's the name of the chip there, as you can see, 737 underscore AC detect, right, and it is coming to pin number 6, and this voltage is about, anybody can tell me how much voltage is this again? All right, so it is roughly 2.6 volts. So 2.6 volts coming to here, and it is going to pin number 6 as adapter detection. So let's go back to the pin definition of AC detect. Right, adapter detection input pin. Right, it's a program adapter valid input threshold by connecting a resistor divider by adapter input AC detect to ground. When AC detect is above 0.6 volts VCC, and when VCC is above under voltage lockout, RGE and LDO is present, ACOK adapter, ACOK comparator and iode are both active, right. So at the same time, after this 2.6 volts coming in, it is releasing an open drain output of linear voltage. This voltage is 6 volts, right. This voltage is 6 volts coming out of this pin number 16, right, and it is coming to be to here, and it is now be renamed to BQ24737 underscore VDD. So this is a power supply to this is a very important voltage. If this voltage is not coming out of this chip, then you replace this chip, right. So first we check VCC, right. VCC is coming, 18 volts is coming, right, to this charging IC, VCC, then AC detect 2.6 volts, then immediately you should check pin number 6. All right, so let's go. So you should check pin number 6. So let's continue checking the working conditions. So RGEN, let's go back to the data sheet. REGN, let's go down to where we find it. Linear regulator, REGN, is the output of 6 volts linear regulated supply from VCC. The LDO is active when the voltage on AC detect pin is above 0.6 volt and VCC voltage is above. On the voltage lockout, you should connect a 1 microfarad capacitor from RGEN to ground, and this is the capacitor that they are talking, this 1 microfarad capacitor, as you can see, and it is connected and it becomes PQ24737, right? So once this is okay, then AC OK will release. This is ACPRN. This is a low logic voltage. On some boards, this voltage will be high, will be pulled up. It is normally pulled up externally by a resistor. And let's go to the data sheet of this pin again. ACOK. Let's go to ACOK pin. As you can see, ACOK, adapter detection, open drain output. It is pulled high to an external pull-up supply by external pull-up resistor when the voltage on AC detect pin is between 2.4 volt and 3.15 volt, and the VCC voltage is above under voltage lockout protection, right? This will release and this signal be pulled up by 3 volts. But on this board, it is not pulled up, it is low. This is a logic low because, as I said before, this because of these 2 p-channel MOSFETs. As you can see, these are 2 p-channel MOSFETs. So let's go to the whereabouts of this signal. So this voltage, first let me just copy the signal and see where it's going. All right, very important, BQ24737 underscore VDD. This is a 6 voltage, 6 volts. All right, and let's see what the schematic has for us. Alright, so it's going to this section here. This is on the charging IC, still on isolation protection. Let me zoom out for you can see. As you can see, here's the charging IC and here's the signal. Alright, and it is coming to this pull-up resistance, as you can see. So ACPRN, this is coming from our adapter pin from the charging IC pin number 5, right? So pin number 5, ACPRN, is coming here. As you can see, it's coming to here to this MOSFET. This is a 2-in-1 MOSFET, so you can say PQ998B, right? And the other one, I think it's all the way over here, PQ998A, right? PQ998A, right? And here's the other one, PQ998B. So ACPRN is coming to this to the gate. So this is an N channel MOSFET, as you can see. So this voltage is 0 volts coming in, right? So this will cut off. It won't conduct because it will conduct ground, and then this resistor would burn if this, because this is 47k. In order to protect this voltage, you have to put a 100k resistor here. If this was supposed to be conducted, they would put a 100k resistor here to act as a protection to protect this voltage. So 47 kilo ohm, this voltage, this resistance is too small, so when this ground come here, it will go through and hit the charging IC, and then this signal, the signal BQ724, the charging IC, will be damaged. So there is no way that you can make this conduct. So that is why this is 0 volts, right? So this is 0 volts coming here. Sorry, so this is 0 volts. It's kind of a bit difficult to draw with the mouse. So this is 0 volts coming here to pin number 5, which is the gate, right? This will cut off. This will cut off. Now this voltage BQ737, 6 volts. As I said before, this is 6 volts, and it's coming through. And it's coming here. At the same time, it's coming through another voltage divider. So PR27, so PR273, PR372, P27, sorry, and PR333, right? PR333. So these are 2 voltage dividers. One is connected to the supply, and this is connected to the ground, right? And this is coming in, and at the same time, it's conducting. So this is going to pull to about 3.2 volts, right? So let me get my voltage divider calculator, so we can calculate this resistance. Okay, so this is coming here. Alright, so I'll open the voltage divider calculator and we will get to the calculation. Alright. Alright, so here it is. So we have an input voltage, it's 6 volt, and our first resistor is 12k, and our next resistor is 10k. Let's calculate. Beautiful. 3.27 volts coming out of this voltage divider. So this voltage divider is releasing this pulling this 6 volts to 3.2 volts, right? And it is being renamed to AC in, right? And our next signal, and then we have PAC in. So it's two signal coming out of this this small circuit, very powerful circuit, beautiful circuit, right? So this is going to the IO controller, page 44, and this is going to this is our key signal that we are looking for, PAC in. So this is the birthplace of this signal. So this is the birthplace of PAC in signal. So let's copy this signal and see where it's going. This is a characteristics of the compound motherboard. So PAC in, right? So PAC in, and it's coming to here, PAC in, PAC, here it is. So PAC in, as you can see, is coming to this section, as you can see. So PAC in through our resistor here of 47 kilo ohm, right? And it is coming to, this is 3.2 volts. As you can see, this is a N-channel MOSFET, right? And it is coming to the gate of this N-channel MOSFET. At the same time, this MOSFET will conduct. This MOSFET will conduct here. So this will conduct, right? This will be 0 volt. This will be grounded. The ground will shift, come over here. So PR307 of 68 kilo ohm and PR303 of 200 kilo ohm, and this will conduct. So this 19 voltage coming in will be 18 voltage will coming in, will be pulled down low to 6 volts, and it will be coming here to conduct. And this is 6 volts coming here, and this MOSFET will conduct, right? And it will produce the B plus rail, right? At the same time, it produces P3. So P3 is produced, right? And the common point is then produced. This is the common point, 19 volt rail, or your 18 volt, or 19 or 18. From a battery, it is 11 volts. From adapter, it is 19 to 18 volts. Right, keep that in mind. So this is your common point. So both voltage come to this source, right? In newer boards like the Dell, in newer notebooks like the newer Dell Latitudes, this voltage is broken, is then pressure dropped through the charging circuit like the Apple to become 8 volts, right? So it's 8 volts for the entire 19 volt rail. So the whole board is supported 8 volts. So it takes this 18 volts. After coming through this circuit, it is dropped, the pressure dropping it to from 19 to 8 volts. These are for the new notebooks. For the Apple PC, this is always the architecture, right? The Apple charger is 18 volts coming through the isolation protection circuit. The charging IC then break down that voltage to about 12 volts. If it's an Air, then it is 8 volts. MacBook Air, MacBook Pro Retinas, those are that type of architecture, right? So they are now included into the PC. I mostly see them on the Dells, right? The Dell Latitude, the new Dell Latitude with the Skylake and the KB Lake CPUs. All right, so this is conducted. So this is 6 volts, and this becomes 18 volts is produced, and the common point B plus rail is created. So let's go to the diagram designer. So we're gonna draw the charger page. This is our charger IC. Alright, I want a thick width. Okay. Alright, so this is our charger IC, and that's called PU301. Alright, and that's called, our IC name is Alright, so this is our charger IC BQ24737, right? And we have our VCC pin first, Right, so VCC pin, let us rotate. Right, VCC. Next we have AC detect, paste, then next we have our RGEN, then we have our ACOK pin output, alright, so let's alright. Okay, so V in, and then this produces a P2. Right, right, and we call this P2. Alright, so P2 was generated from here on the schematic. Alright, here P2, and it's on this side rather. And on this line. Alright, VCC. Alright, just to keep it reference neat, same size. I won't draw this anymore. It's annoying. I'll just keep it as is. Alright, so this is part 1. This is part 1 also. Alright, so we have from V in line, there's another voltage coming in. Let me zoom out a little bit. This is the V line. Alright, so this is coming through 2 resistors. connected. This is grounded. This is the second step. And this is the linear coming out. This is also a second step. This is the third step. Right, and this signal, as you can see, and this is the third step. Alright, so as you can see, I'm creating a timing here, as you can see, for step-by-step easy reference. Alright, so these two MOSFETs are generated by PQ 307 This is a 2-in-1 MOSFET, as you all see. And it's going to control let me just carry it down a little bit. Alright, it is alright, and the ending of this part is connected there. Alright, so it's almost finished, and this is your PAC in signal. And this is our fourth step. Alright, that's the fourth step. Alright, and then the common point voltage will be created, and that's the fifth step. and this is the B plus. Sorry, I'll call this is our B plus point, common point. Right, good. Okay, so this is the process. Okay, so let me explain. All right, so if we are inserting the adapter, this is adapter interface. Right, first step, going through this MOSFET to produce P2. At the same time, P2 is providing power for the charging IC, right? And then we have adapter detection, right? Then we have the output of the linear voltage, then ACPRN or low voltage to generate PACN, and then it is conducting these two this MOSFET. This is part B of this MOSFET, and these two MOSFET will be conducted to output with B plus point. So this is pin on part number 4. Alright, this is part 5. Okay, let's go back to the schematic. Alright, so this is conducted, and these two MOSFETs are conducted, and it is producing B plus. Alright, so B plus is produced. Next, we'll go over to the battery section. So in battery mode, if in battery mode, then this voltage will not be present. Right, this voltage will not be present in battery mode because it's battery, it's in battery, so the battery will discharge. Now this signal AC off, this is a signal that is released from the I/O controller. So let's say you have battery and adapter inserted at the same time, right? So what will happen is that the battery will be fully charged and the battery needs to be discharged. So in order to discharge the battery, the I/O controller will read the battery information through the SM bus lines. These two lines is the EC SM bus clock, EC SM bus data, and when these two signals are being, when this charging IC and the battery is communicating with the I/O controller and the battery is full, then the I/O controller will immediately send the signal AC off or adapter cut off. So what will happen? This signal will come to here. Now this signal is a high signal. This is 3 volts coming to this PQ998A, right? Remember, this is part A, right? And part B is controlling the production of AC in. This is part B. Remember, I have already explained the signal, right? So this is cutting off. This is to generate adapter detection, and this part PQ998 is to generate adapter detection to the I/O controller. And part B of this MOSFET is now what is it doing? It is now telling the charger I/O controller to cut off the adapter. Now we need to run in battery mode. So this ACR signal comes to this NPN MOSFET. This will conduct, right? This will cut off, right? At the same time, this is with 0 voltage, so this won't come in, because if it was 0 volt, if this voltage was coming here, then this AC in, PAC in will come here and it will damage this MOSFET. it will damage this MOSFET, right? It will damage it because the ground voltage is coming here at the same time, coming here and hitting this MOSFET, right? Because the resistance is too small. It would have to be 100 kilo ohm resistance, right, to protect it, right? So you would have to put a 100k resistor here in order for it to be protected, right? Here would have to be 100k, 100 kilo ohm resistor, and they put a 47k. So that is why this must be cut off. So this is conducted. Here is pull low. This is 0 volts at this time, right? So the adapter is not inserted. This should be pull low. This is protect. So 47 kilo ohm, right, is here to protect this, but it's not as efficient as 100k. So what will happen is that the battery will become PAC in G. So PAC in G, let's copy the signal, right? When this AC off underscore 1 comes to this MOSFET, this will conduct, this will be 0 volts, this MOSFET will be cut off, right? Automatically 19 volts will flow through here, right? And it will come here, right? 19 volts will come here, this will cut off, right? Right, so this is your AC FET. Remember, this is your AC FET. This is your AC FET. Okay, so this is your AC FET, and that will cut off your adapter, hence here no voltage. Okay, and that's the process of the adapter cutoff. So when this signal comes to here, this will be grounded, and this MOSFET will be cut off also, because this entire section will be grounded, right? So this entire section will be grounded, so this MOSFET will be cut off, right? And then as you can see, this is a 200k resistor, and this 200k resistor is coming here, right? And this voltage is coming to stop here, right? So these two small resistors are acting as a protection, right? So these are two transistors. We have this is a P, this is a N channel transistor, right? And this is a P channel transistor. So in my class of electronics foundation, I'll teach you how to identify an NPN transistor and a PNP transistor, right? As you can see, the base, right, pin number 2, which is the base, right? This is the emitter, right? And this is the collector, right? As you can see, so the base is coming here, so 18 volts coming here, 19 volts coming here through this 200 kilo ohm resistor. As you can see, this is a what? This is a NPN. This is a NPN transistor. So this will conduct, the ground will shift over here, right? This is a NPN transistor, so this will conduct. So this voltage will conduct and it will flow from here to here and pulling up here, as you can see, and it is acting as a protection, right? That's it. So this is a beautiful circuit designed by the Compal industry, right? And this protects the adapter for discharging and charging of the battery, right? And to cut off adapter when the battery needs to be discharged. Okay, so this is the isolation and protection circuit, as you all know, right? So when this, so let's copy this signal. All right, so this is produced here. Oops. So let's copy this signal. It's PAC in. Sorry, it's called PAC in. Let me just delete this out the way. All right, so it's called PAC in underscore G. Alright, I'll just put the P there instead, it doesn't matter. So I'll put the P. Let's see where that signal is going. Alright, so that signal is going to only here. Only here. So this signal is only found on this page. So let's go over to the battery section. As you can see, PAC in is coming to this MOSFET. This is a NPN MOSFET, right? It's the N channel MOSFET, and it's coming here. And this MOSFET is conducting ground, so this will be grounded. This will conduct ground, as you can see, and it's producing PAC in P. PAC in P is coming. This is grounded through this diode. As you can see, this MOSFET will be cut off, right? This motors will be cut off, right? Cut off, right? And as you can see, V in is coming through this 47 kilo A resistor. This is in adapter mode, and this voltage will come to here, and this is the battery isolation MOSFET, and it will cut off because a P channel MOSFET. So 18 volts will be here, right? 18 volts will be here, and therefore this is a P channel MOSFET, so the voltage at the gate is the same as the voltage at the source, so it will cut off. So in battery mode, when the battery needs to be discharged, as you can see, there's a signal here, discharge G_1. So this signal, so V in is not present because V in is coming here if the adapter and the battery is plugged in at the same time, right? ACLU1, which is a high voltage coming through this diode, right? After coming through, it becomes PAC in, right? And it is conducting. So what will happen? This will become a voltage divider. So PR305 and PR304 become a voltage divider, and this is pulling it down to roughly about, say, right, that's 10k and a 47k, right? So let's do the calculation. So that's 10k, so we have 18 volts, we have 10k, and the other one is 47 kilo ohm. Let's calculate. So that's 3 volts, so 3 volts coming to here. So that's 3 volts coming to here, and this battery will what? Discharge. As you can see, the diode is forward bias, so the battery voltage will come pass through and the battery will discharge, and that will produce the B plus, which is also the common point. As you can see, it's connected, right? And for EMI request, also for filtration, right, there's a coil, right, for EMI requests, as you can see, right, to filter any noise and ripples from the outer environment during your usage of your laptop. Alright, so this is the complete sequence of the isolation and protection, right? In the next class, we're going to look at the EC standby. We'll look at the standby section, EC standby breaking conditions, right? And the generation of 3 volt and 5 volt, which is the standby analysis. That's on the next class in next week. As I said before, these classes are this class I'm giving the entire sequence, and it is free of cost, right? This class I'll just give you as a reference. Let me just finish sketch up this diagram. So this is the common point real is being generated, and I'm going to just get the battery MOSFET. Okay, see the battery MOSFET. Let me just sorry, let me, I will just rotate. Alright, so this is our battery MOSFET. Alright, and we'll just draw a box here. And just increase the thickness of the line. BATT plus. Right, that's the name of it on the schematic. Yes, BATT plus. Alright, so let's bold, and then this is our battery interface. Alright. Okay, and this is controlled by PQ308B. And alright, and this is controlled by ACLU1. Alright, so that's the steps. So let's give this this is Lenovo G0. This is NM-272P timing analysis. And I'll give it a size 19. Right, so let's save this. Lenovo G50. That's NM G50, and that's an NM-272P full timing analysis. Okay. Alright, so next class I will continue with the EC and the standby conditions for the IO controller. Alright, so we'll look at the EC and standby working conditions of the IO controller 3 volt and 5 volt section. Okay, thanks for watching.